Oh man, so let's talk about something called the complex conjugate root theorem, which this all relates back to the fundamental theorem of algebra, which states the total amount of zeros that you end up with should equal the degree. So when you combine all the real zeros and all the imaginary, they should always equal the degree. Don't ever forget that. Okay, so this is going to be example 1 in your handy dandy notebook, which what I want you to do for example 1, I have worked out example 1 for you. Okay, so you are literally going to copy all this down for example 1, but what you need to think about is what did I do to get from my first step to the last step, because typically what happens, what this says, you guys, it says write in standard form given the roots. So I've given you roots, which remember roots are the same things as zeros, x-intercepts, or solutions. Okay, so I've given you the roots, and what we have done is worked our way to standard form. Now typically, what we've been doing so far is we've started from standard form, which the last one's standard form, that's your answer technically. Typically, we started in standard form and worked our way to find the zeros, or x-intercepts, or roots. Okay, so let's just refresh what we normally have been doing so far to get from standard form to our zeros. So we start in standard form, then typically we skip to this step, which what we do to get from here to here is we have to factor. Okay, which the factoring technique we would use on this one, since there are 3 terms, typically the factoring technique is slide and divide, or remember if you don't like slide and divide, technically if you don't like slide and divide and you just did the quadratic formula on this, you'd get your answer, which are the roots. Okay, but if we're using factoring, we'd factor this and get to this step through slide and divide. Then after that, to get to this step, remember if 2 things multiply to equal 0, at least one of these has to equal to 0. So we set each factor equal to 0, and that's through the zero product property. Okay? Then after this, we just simply, to get to our final step, would solve for x. So we'd, add 1 on both sides and get positive 1, or subtract 3 on both sides and get negative 3. Okay, or the shortcut, you guys, remember from factored form to our zeros, all you have to do is change the sign of the 0 in the parenthesis. So technically, we could skip this step right here. Okay, we could instantly go to the last step from this step. So we could go from here all the way to the last step just by changing the signs. So that's what we've typically done. Okay, so in class we talked about, or actually you talked about with your shoulder partner, what we did to reverse the process. So how did we start from the roots and get to standard form? Okay, which if you were not in class to do that, I want you to do that on your own. So in your handy dandy notebook, you're going to write the steps starting with the roots and getting to standard form. And I want you to tell me, how did I get from this step to the next step, to the next step, to the next step, and to the final step? So kind of reason through it, because in this section, we're going to be given the roots and have to get to standard form. But we're going to have to step this problem up and throw imaginary numbers in the roots. So before we do that, though, we need to perfect how to do it with just real roots. Okay, so if you were not in class to do this, pause the video and write down what you think we do to get from one step to the next until you get to the last step. Okay, guys, so in class we talked about this, but I'm going to help you reverse the process. So this is where we'd start. These are our zeros. Then to get from our zeros to the next step, we basically bring everything from the left-hand side, from the right-hand side to our equation to the left-hand side. So like when we bring negative 3 to the other side, we have to add 3 to get it on the other side, and it becomes x plus 3. And same here. When we have a positive 1, the way we get it to the other side is by subtracting a 1. Okay, so we move everything from the right side of the equation to the left side of the equation. Alright, then to get from here to the next step, we just write our answer in factored form. So these are each of our factors, and we set those bad boys equal to 0. Then to get from here to here, you probably already know, we distribute. Okay, we take x multiplied to x and 3, and then take negative 1 and multiply it to the x and 3. Because x times x gives me x squared, x times 3 gives me 3x, negative 1 times x gives me negative 1x, and negative 1 times 3 gives me negative 3. And finally, to get from this step to this step, we just combine our like terms. Guys, so this is the basic process we're going to be using once we have our roots to get to standard form. Now, there is one step that you can skip in this process. Technically, we don't have to do this step. Technically, I could go from my very first step to this step. And the shortcut to get from your zeros to factored form, just kind of reverse what we did over here. You change the signs. So since this is a positive 1 in factored form, it's x minus 1. And since this is a negative 3 in factored form, it's x plus 3. So technically, if you want to start from here and go directly into factored form, I highly encourage it because math is all about being as efficient as possible. Okay, so hopefully this was an enlightening experience because now in the next example problems, we're going to step it up and throw imaginary numbers in the mix. But before we do that in class, we're going to do an awesome funsy, so you'll have to wait for that. Now, before we talk about how to write in standard form giving complex roots, which the word complex means imaginary roots, and a complex number is in the form a plus bi. So the a is kind of the real number part, and the bi is the imaginary part. So complex roots, you guys, kind of combine real parts and imaginary parts, but they are ultimately imaginary numbers. So what the complex conjugate root theorem states. Okay, if a plus bi is a root, so this is a complex number, a real part and imaginary part. If a plus bi is a root of a polynomial equation, then a minus bi is also a root. Sorry, guys. Holy hot dog. Okay, so if you have a root, you should have two imaginary roots if they are imaginary, always. Okay, imaginary roots always come in pairs. And I like to call them the evil and the good twin. So they come with a positive root and a negative root. So the good twin and the evil twin. So if you're a twin and you're watching the video, you have to figure out, are you the good twin or the evil twin? But anyways, so imaginary roots always come in these cute little pairs as a positive one and a negative one. Now, some things to consider with complex conjugate roots. Okay, so again, imaginary numbers always come in pairs, which are called conjugate pairs. Okay, and the conjugate part means one of them's a positive and one of them's a negative. Now, be careful. You only change the sign of the imaginary number. Okay, if you look up here, the A didn't change. A stayed as positive A. It was positive A and positive A. The only part that changed was the I part. It went from positive BI to negative BI. So do not touch the real component of the complex root. Only the imaginary part changes from positive to negative. So some examples of conjugate pairs, you guys, are 3i and negative 3i because they have changed signs. And be careful, negative 2 plus 4i and negative 2 minus 4i. You guys see here, the negative 2 stayed the same. Do not touch the real parts. Negative 2 doesn't have an I with it. Sorry, it doesn't have an I with it, so it's a real number. So we don't change the sign of the real number, only the imaginary numbers. See, positive 4i changed to negative 4i. So be careful. Okay? Alright, so I know you guys are excited to start writing this in standard form with complex roots. Okay? So it says write the polynomial in standard form given the following roots. Okay, so example 2 is a degree 3 polynomial. Which remember, you guys, the fundamental theorem of I cannot talk today, you guys. Good golly. The fundamental theorem of algebra states that the degree should always equal the total amount of roots. So if we have a degree 3, we should have 3 roots. Holy hot dog, though, you guys. We only have 2 roots. X equals negative 4 and x equals 4 plus I. So something is going on. We only have 2 roots, but we're supposed to have 3. Okay, I have 1 real and 1 imaginary. Let's talk about the imaginary part. Let's think back to here. Imaginary roots or complex roots always come in pairs. Okay, so if you see here, we are missing one of the imaginary roots. We have the good twin, the positive I, but remember, there should also be a 4 minus I. So I'm going to do this to you guys, and probably I will do this to you on your test. I will not give you all the imaginary roots because you should know from the complex conjugate theorem that imaginary numbers always come in pairs. So I might leave one off and you have to remember that they come in pairs. So if you have the positive one, the negative one's missing. Or if you have the negative one, like in example 3, the positive one's missing. Okay, so say with example 3, I have a degree 4 polynomial, which means, based on the fundamental theorem of algebra, that there should be a total of 4 roots if you're done. Which if you see here, my roots are -2 and 5 and -3i. Holy hot dog, you guys, this degree 4 is supposed to have 4 roots but only has 3. I currently have 2 real roots and 1 imaginary. But remember, you guys, imaginary numbers always come in pairs. So if I only give you 1 imaginary root, there is secretly another root hiding out. So if you see here, I've given you the evil twin, the -3i. So you're missing the positive version, the positive 3i. Okay, so be careful. If you ever end up with only 1 imaginary root, or if I only give you 1 imaginary root, you need to reevaluate the problem because one of them is missing. Okay, so go ahead and pause the video and watch example 2 and 3 and find out the magical things that happen when you have complex roots in the problem. That's not what I meant to do. Jeez Louise. And this will be a funsy, so you have to wait on this later, you guys. And that's it, you guys. It's been awesome.